Does it work?
Not yet. I'll have to work on it. But I won't have time right now. But it shouldn't be a problem, I think. Okay, guys. Can everyone see?
Yeah.
Yeah? Let's turn off a little bit more lights.
Yeah.
So today we begin to introduce the idea of simulation. And for now, we're going to focus our attention on gazebo, but we're going to go slowly. There's a lot of things for us to learn, okay? So, let's start with the motivation. Running experiments with real robots can be difficult for many reasons. Setting up a complex robot can take a lot of time. You have to start a lot of files, a lot of notes, got to take care of the physical environment. Got to get the robot ready to start. It could take you 10 minutes, 20 minutes, sometimes 30 minutes just to get started. Yeah, in the right way. It depends on the complexity of the task. Sometimes you may be using more than one computer. So either one person is moving around, setting up all the computers, or you have a team of people saying, this is ready, this is ready, this is ready, or just checking. And to make all of that work very seamlessly, it takes a lot of work. And that may be just for one experiment. If you want the robot to be very robust, very general, very flexible, it just takes even more work. Yeah? Robots can be fragile. Fragile, that means they can break easily. If you make a mistake, hit a table, things can break. A motor can break. A physical part of the robot can break. Like some of you guys have been doing force control and get a little bit scared when you have to work with the real robot, right? And I showed you some experiments with, if you have a controller and it's not stable, the robot can start to do things like this and hit something. Yeah, so they're fragile and they're expensive. So if you break anything, the cost of that, the pain, the difficulty is really big. So there's a lot of motivation to use simulation. Simulations can run quickly. Yeah? You can change them much faster than you can a real physical robot. Most of the time, not always. Yeah? If you break anything, it's free. You just start it again and run it. Okay? Now, good simulators, this is important. Good simulators require no change of code from software to hardware. Yeah? That's a good simulator because you can run the same code. And for the longest time, this was not possible. It was really difficult to get a simulator and a real robot to run exactly the same way. And with ROS, this can be done seamlessly for many, many robots. Exactly the same code can run for software and hardware. You may not appreciate that because you have not experienced the pain, but that's very valuable. Yeah? And simulators, you have simulators that run with physics engines. Physics engines. There are simulators that run without physics engines. The simulators that run with physics engines resemble a real world. Yeah? You can resemble sensors. Not perfectly, but similarly. You can resemble actuators. You can resemble the forces and the moments that happen when you make contact between a robot and an object or a surface. Yeah? You can experience gravity. You can experience acceleration. You can experience forces. That's what a physics engine lets you do, okay? You can feel weight and mass and momentum, okay? So ROS is really well suited for this. Just to introduce the idea of a simulation, we can start with a very simple 2D environment of a robot. Yeah? There's no physics engines here. This is an example of a maze or a map. And there's a package called 2D Robot Simulator, or STDR. You can click on that, and you need to download it using sudo apt-get install ROS Indigo STDR Simulator. Once you download it, you can just easily run it by saying ROS launch, std launchers, server with map and GUI plus robot.launch. Okay, so let's do it real quick, and you do it with me, download it, and then run it. And let's take a look at it. Okay. ROS launch, stdr, launchers, server with map and GUI plus robots. So you do that. You have the PPT. You can look at it in your own computer. Yeah. And so here's the simulation. All right. Some of the things we can see right here is that the robot contains a LiDAR. LiDAR is like something that combines light with a sonar. Yeah. And and the red color, you see the LiDAR. Yeah, it's a ray of light that goes away from the robot, and anytime it hits a reflective surface, then that ray can come back, and you can have an idea of the distance of that surface. Some surfaces like glass or shiny metal, or this floor, for example, those are surfaces that don't reflect very well, yeah, depending on the angle as well. So the light ray might hit a window and not bounce back, just keep going or go somewhere else, so you get bad information from that. It works best with walls and hard surfaces. Yeah, the green color is, I think, for sonar. Yeah. Now, both of these sensors have some limitations. They can't go on forever. Maybe they can measure distances within a range. That could be 1 meter, 2 meters, 10 meters, depending on the sensor. So if you hit a surface within that limit, it can go back. You also have a field of view for all sensors. For example, you have a span of about 30, 40 degrees here. The sensor may not be able to measure 365 degrees, 180 degrees.
I can find a page for those via STO.
Are you new to our class? Have you been coming every week?
I can come here last week.
So it depends how if you have set your ROS server address and ROS keys correctly, should be able to find it. I don't know if you have done that. Yeah, that I cannot help you with that just now. I can help you that in a break. Yeah. And so this is a mobile robot, and by default in ROS, we can move mobile robots by commanding a twist. You guys remember what a twist is? You should know very well. What is a twist? I see these kinds of faces. Like. Quick? No? No? That's all right. What? What kind of message? What kind of vector? Oh, come on, guys. Well, it's right here. Linear velocity and angular velocity. Twist is about velocity. Linear velocity, angular velocity. So you can move straight, x, y, z, or you can rotate x, y, z. Yeah. Now you're a mobile robot. You cannot rotate x. You cannot rotate y. Which x is like this and y is like this. You can just rotate z. Okay, for a standard mobile robot. So once we start the simulator, we can see everything that this little 2D robot is going to do. So you can say robot ROS topic list, right? And you can see there's a lot of things being published here. Yeah. This one is very interesting to us, the command velocity. The command velocity topic is where you command the velocity. You command the robot how to move using a twist. Yeah? And then the other one that's going to be very interesting is this one, the odometry. The odometry is how the robot is moving with respect to the world. With respect to the world. And you can combine simple or advanced techniques here to compute the final odometry. Yeah. So for example, if you say ROS topic type, robot 0 command velocity, you get that geometry messages twist. Okay. And then if you want to see it, you pipe that ROS message show. Yeah. And so here's your linear 3D velocity and your angular 3D velocity. Okay. For the odometry, it's a little bit more complicated. This is navigation messages odometry. Okay, and let's look at what that looks like. ROS message show. You have a position, you have a pose, position and orientation, right? Where is the robot? XYZ, what is the orientation? Then you have covariance because there's a measure of error, yeah, of the sensors. And then you also get a twist on that, how fast is the robot moving. But this is the robot motion, not the command, right? So that's the odometry, okay? Let's go back here. The sensor data from the LiDAR and the sonar can help us to localize. SLAM means simultaneous localization and mapping. Localization is where am I in the map, yeah? When you look at this simulation, where is the robot? If this is 0, 0, right? So you have some distance x, some distance y. And SLAM or localization is about how can the robot know where it is at the beginning. Okay, and then you use that also to avoid collisions, right? You don't want to hit the wall, you don't want to hit other things that are moving. So now we're going to command the robot to move by sending a command to command velocity. Okay, so I showed you that. So here manually we can command a velocity using ROS topic pub, right? ROS topic pub, the first thing that you do here is you take a rate. So this is going to be 2 times per second. Then we have the topic, robot 0 command velocity. Then we have the type of the topic, geometry messages twist. Yeah, and then we need to supply the data. This is a little bit more complicated. You need to learn the syntax, start and finish with quotes. Then start and finish with curly brackets, right? And then you have the linear component and you have the angular component. After each component, you need a colon. So linear colon or angular colon. And then that has a substructure XYZ, right? So you have X colon, and here, pay attention, space, 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 space. You need a space. If you don't include a space after the colon, it won't work. Okay, so the syntax is important. Move in the X direction, forward, 0.5 meters per second, 0 in the Y, 0 in the Z, cannot move up. Yeah, and then angular, cannot rotate like this, cannot rotate like this. And here, this is this kind of rotation, we set it to 0. So if we do that, you can move. So let's go here, let's move this to the side, let's bring this over on this side. So you can say ROS topic pub, rate of 2, robot 0, command velocity, geometry, messages twist, quotes, curly brackets, linear, colon space, yeah, X, 0.5. Actually, if you only want to send one command, you can just stop there. Everything else will be 0 by default. Yeah, so you press enter, and the robot begins to move. Okay? So right now, the robot is getting this command. That command goes into the PID controller. That PID controller sends the command to the wheels, begins to move, and then here it hits the wall. Okay? If you want to move it back, you press Control-C, just change that to a negative number, and it'll go back. You see the sensors reflect the shape of the map. Okay? You can also, if you want to stop, you can publish 00 or even an empty message completely. Okay? So ROS makes it very easy to handle a robot. Okay? Then we can do the same thing using C++ code. Yeah. Let's look at this CPP file. There are going to be ROS headers. We'll be publishing the command, which is a twist. We need to set those values or parameters. Setting some parameters, filling the twist message and then publishing with some hard code loop. So here what the robot will do is like go straight and then go left. Very simple code. This one is in part 2. So let's see. We can come back here and say ROS ed. And is it part 2? No. Let me see. Let me open this code real quick. Remember what I should have put a ROS ed command there. This is stdr control. Okay, so we go to stdr control, and then stdr openloop.cpp. So here's our code. Let's take a look at that super quick. Of course, ROS.h, and then because we need to publish a twist, right? Geometry messages twist.h. We need to define that. We need a definition for the ROS message. This is a geometry message twist.h. If you feel confused, you need to remember, I need to become familiar with types. Yeah, and then know which one to include. So we init the node, we create the node handle, and here we have the publisher. We're going to publish a geometry messages twist. This is our topic, and then we have a queue of 1. Here's some parameters. The delta t, the time that we're going to use for this math, 0.01 seconds. We want the robot to move at 1 meter per second. We want the robot to rotate at 0.5 radians per second. Remember that in ROS, all the units are standard units. Meters, seconds, radians. Okay? And then some threshold for moving 3 meters, something like that. So then, because we have that .h header here, we can just set everything to 0. First, we need to create the variable, right? Geometry messages scope operator twist. Then you give any name you want. We're going to call it twist command. Once we have twist command, we can access the linear and the angular parts of that message. Both of these have XYZ, right? And then you set them to 0. Okay, so in terms of rates, we learned that before. We create this variable loop timer. And this is going to be 1 over delta t. Delta t 0.01, so the rate is 100 hertz. Okay? And then start the timer at 0 here. And this is just a hard-coded for loop. So we're going to do this 10 times. We're going to publish the twist command. At the beginning is 0. And then we're going to sleep to make this 100 hertz. So right now, the robot will not move, right? Everything is 0 and we're not changing anything. After that, we change that message to speed. Speed we set up here to be 1 meter per second. Yep. And so while timer is less than 3 seconds, publish the twist. So this is, let me see. This is setting the linear.x part of that twist message. So it's going to move forward 1 meter per second. It's going to do it for 3 seconds because we're publishing. Yeah, we increase the time by 0.01 every time, and eventually it will stop. So this is just a hard-coded way to say, move forward, 1.0, publish, increase the time, control the for loop rate, and then, or the while loop rate, and then come back. Yeah?
Why do we use while loop?
Because we want to run until 3 seconds has passed. Until 3 seconds has passed. Then we stop the robot. Now we make it rotate. We set angular.z equals yaw rate. Again, we set the timer, same while loop. We're going to publish that twist, only has a rotation. Increase the time, control the rate of the loop. And then set both to 0 and publish that. So, you have the code. Make sure you run catkin make. Once you have that code, then we can run this. Yep, let's look at our simulator. And actually, let me move that robot back a little bit so it's at the beginning where it used to be. Maybe I'm going to mess this up because it's in a different location. But now we can say ROS run. Russ run this one. I think should be this one. Yeah, this one. We also need Russ core. No, we don't need Russ core. We have that. So we run that, and there it goes, moving forward 1 meter per second, 3 seconds, and it rotates, and then goes again, something like that. Hard-coded way to do it. All right? All right, so let's go back here, full screen. Oh, what happened? Okay, so of course more intelligent approaches can be used. We have another book in the class called Ross by Example, book number 1, book number 2. Book number 1 also gives you a nice SLAM overview, and then book number 2 gives you kind of pretty advanced examples, charging velocity, moving autonomously using state machines. So you can look at that if you want to learn more. But even something as simple as this can be useful for simple sensor-based behaviors. Very simple sensor-based behavior. I have a student, he's looking for a job at Dorabot in Shenzhen. They use a lot of ROS. They asked him a question about, hey, how can you navigate through this map? Give me your answer in 30 minutes. He freaked out, he didn't do it. You can do a lot of things with simple sensor-based behaviors to navigate. That could give you a job at Dorabot if you know how to do this. Okay? Here we don't have any sensor noise, so that means that sensor information that you get is perfect. But you also don't have realistic vehicle dynamics. This word can often confuse students. Dynamics. What does that mean? That's the way in which a robot can move, especially things related to physics. So the robot has inertia, right? You start accelerating, and then if you stop moving, the robot still wants to move, right? So you have to apply brakes or something. Same for an arm. Those things affect the motion of the robot. You have angular inertia, that has to do with rotations, right? Actuator saturation. Saturation here means, let's say that you want just like this, ED. Stand up. Now I want you to put your hand back here. Don't move. Yeah, just put your hand, touch my hand. Touch my hand back here. More, higher. That's saturation right here. You can't move more because you reach your limit. Motors have limits. When they reach the limit, they saturate. Yeah? Everything has a limit. Yeah, you cannot go further back than this. This is actuator saturation right here. You have friction. They're motors, they're metal, right? They need oil inside, there's friction. They get hot. Servo controller, the controller response cannot be perfect. PID controller, you see, some of you guys have been doing PID controllers, you see that they're not perfect or have mistakes. The response affects the dynamics. If you have a car, a mobile robot, the wheels can slip on the floor. They rotate, but the car didn't move. Because they slip. Sometimes they slip, depending on the terrain. And here we can just look at, we call it the dynamic response, although the only thing we're going to look here is at the twist. We can look at the dynamic response using RTT plot. Yeah, this is a Ross, Ross standard is to publish the robot's linear and angular velocity as odometry. So when we use RTT plot, we can look at the odometry topic and pay attention to the twist part of the odometry topic. So let's go back to here. I still have my simulator. Let me start it again from the beginning. Let me open one more here. I'm going to take this off, put it over here. Let me close this. We're going to do this on this one. Yeah, and we're going to do the simulator here. And we're going to say RQT plot. Robot 0. Let me see, this still doesn't exist. Let's start the simulator. Move it here. Robot 0, odometry. Yeah, twist. Should just be one. I think here I have two twists. That's wrong. Angular Z. You can always add the signal directly here on the panel. Okay, let's run this node and then let's see this response. And so this blue one is this is showing the position, not the angular response. Or maybe I do need two twists. Can I reset this guy? Reset. This is to load the map. Different properties. Maybe I'll start it again, and then let's do two twists here. Twist. Okay, start that, start this. And it still didn't get it. Robot 0. Oh, let's see. First topic list. Robot 0. Odometry. Yeah, and then ROS topic, ROS message show, nav messages, odometry. Nope, not this one. ROS topic. Oh, sorry, need to do it from the beginning. ROS topic type, robot 0, DOM, ROS message show, odometry. Twist, angular. Okay. twist. Oh, that's what we did, right? Rodems. Twist, angular Z. There it is. Any little mistake can see. So this is just you see the rotation there and the rotation back. Very simple, but you can look at more advanced things with this visualization.